Hi everyone, today a video on carbonyl group chemistry, specifically looking at aldehydes and ketones. So the carbonyl group consists of a CO double bond, and it's present in aldehydes and in ketones. They both contain a CO double bond. Aldehydes have a hydrogen attached to the carbon of the CO double bond, along with some kind of carbon-based group, an R group. So we can write these down as RCHO. And ketones have two organic groups, two carbon groups, attached to the carbon of the CO bond. So we can write that down as R2CO. So they both look very similar, just that an aldehyde has a carbon group and a hydrogen attached to the C double bond, the carbonyl group. A ketone has two carbon groups. Now aldehydes are named using the suffix -al at the end of the name, and the carbon of the aldehyde, the carbon of the carbonyl group, is counted as part of that chain. Now an aldehyde can only occur at the end of a chain because it has a hydrogen attached onto that carbon, and so a numbering system for aldehydes is redundant. We don't have to number where the aldehyde is because they'd always be on the first carbon. So some examples over here on the right. The first one is butanol, so we look for our longest carbon chain, remember. Here it's 4 carbons long, and because our aldehyde has to be at the end of the chain, we don't have to worry about numbering it, and so it's butanol. The next one along, this one's now drawn in the skeletal formula, but it's still the same naming conventions, and so we look for our longest chain. Here it's 5 carbons long, and we also have some branching of the chain, so we have a methyl group was present as well. The aldehyde is always going to be the first carbon, that's the priority of this molecule, and so going along from right to left, our methyl group is on the 4 position, so this is named as 4-methylpentanol. Now the standard IUPAC naming rules apply, so if we have multiple of certain substituents, we have to write them using di, tri, tetra, and we number every single substituent, and we name everything in terms of alphabetical order, not numerical order. And then finally, the last example, the simplest aldehyde there is, methanol. So 1 carbon length in the chain here, just the carbon on carbon itself, and so having 2 hydrogens attached is also an aldehyde. And so this is methanol. Now sometimes we name them slightly differently, so the one to watch out for here is benzaldehyde. So it's if we have a benzene ring attached, and off one of the carbons of the benzene ring we have our aldehyde group, our carbonyl group, and this is counted as a derivative of benzene. So you'll see it called either benzaldehyde or benzene carbaldehyde. Ketones are named using the suffix -one, so -one goes at the end of the name. And like aldehydes, the carbonyl carbon is counted as part of that carbon chain. Now, because the carbonyl group essentially has to be somewhere in the middle of the chain, we have 2 carbon groups on either side. The simplest ketone there is has to have 3 carbons. Now, if we have a really short ketone, such as 3 carbons long, this would be propanone, the first example that we see. We don't need to number where our ketone is in the molecule because it can only be at that carbon. The same for butanone. If we have a 4 carbon long chain, we could put the carbonyl group onto the carbon next to it, but we'd then number from the other side, and it's still technically on the second carbon along, and so we don't need to put a number on that one. However, longer ketones, we do have to number what carbon the carbonyl group is, what carbon the CO double bond is on. So an example here is the final example here at the end, 3-methylpentan-2-one. So again, look for our longest chain, 5 carbons long. Now we could number from left to right or right to left. If we go from right to left, our carbonyl group is on carbon number 4, but if we go from left to right, it's on carbon number 2. And remember that we always want the lowest numbering possible. So we have our carbonyl on the 2nd carbon, so this would be ending in pentan-2-one. And then we have a methyl group substituent as well on carbon number 3, so this is named as 3-methylpentan-2-one. So in terms of the physical properties, the carbonyl group is really strongly polar. We have our electronegative oxygen connected to our carbon, so this gives rise to a very strong dipole, and therefore our delta negative and our delta positive, partial positive and partial negative charges. And so there's permanent dipole-dipole forces that act between molecules that contain carbonyl groups, which means that the boiling points are much higher than those of the comparable alkanes, but not as high as those of, for example, the alcohols or amines, because they have the ability to be able to hydrogen bond, which is a stronger intermolecular force than dipole-dipole forces. Shorter chain aldehydes and ketones can mix with water effectively due to the hydrogen bonding that occurs. If we have water, for example, we have our delta positive hydrogen connected to our delta negative oxygen, and then we have our carbonyl group, which has the delta negative oxygen lone pairs and our delta positive carbon. So we can have a hydrogen bonding where we have our lone pair and our oxygen forming a hydrogen bond to the H plus hydrogen on the water. Now, as the length of the chain increases, the compounds become less and less soluble in water. And that's because the kind of non-polar part of the molecule, the carbon part of the molecule, starts to become bigger and bigger, and it kind of dwarfs and overpowers the polar part of the molecule. And so therefore, longer chain ones are more soluble in non-polar solvents. Now, methanol, the simplest aldehyde, is a gas at room temperature. Other short chain aldehydes and ketones are liquids, and simply because as we get longer chains and bigger molecules, we have greater van der Waals forces, and the intermolecular forces increase. Now, the CO double bond is very, very strong. It's a strong bond. If we look at the thermodynamics of it, the kind of bond enthalpy, it's a very strong bond. However, it's also very reactive. This is something that we call the thermodynamic stability versus the kinetic stability, or the thermodynamic stability versus the kind of kinetic reactiveness. Essentially, we have a bond here that is very, very strong, but it's also reactive. It's strong because we don't just have a single bond, a sigma bond component, but we have a double bond, a pi component to the bond. But it's also very reactive because we have this very strong dipole, the delta positive and the delta negative. And that's because we have our difference in electronegativity, and quite a big difference in electronegativity between our carbon and our oxygen, so a very strongly polar bond. And what this means is that our aldehyde or a ketone can react as an electrophile. We have a delta positive carbon, we have a carbon atom that is electron deficient, and therefore it's going to be able to accept electrons. Remember that electrophiles are electron pair acceptors. And so that means that it can be attacked by nucleophilic reagents. Remember that a nucleophile is an electron pair donor. So our nucleophilic reagent attacks the delta positive carbon, the electron deficient carbon. Now, carbonyl compounds are unsaturated. They don't have the maximum number of carbon-hydrogen bonds they can have, and so addition reactions are possible. And so the majority of the reactions that we will see are called nucleophilic addition reactions, because we add a nucleophile to our carbonyl compound. And so the mechanism is shown here at the bottom, and we're going to look into this in much more detail on the next slide. So as we said, these are nucleophilic addition reactions, and these follow the same general arrow pushing in every case. So it doesn't matter whether we start with an aldehyde or a ketone, or what nucleophile we use, the arrow pushing is always the same. As we said, our carbonyl, our aldehyde or our ketone, because we have that delta positive carbon, our electron deficient carbon because of the CO polar bond, that acts as our electrophile. And then we have our nucleophile. This could be something like a hydroxide anion, a cyanide anion, any kind of thing where we have some kind of lone pair. And so our lone pair is the nucleophilic part of that molecule. We're going to draw an arrow starting from that lone pair, going to the delta positive carbon. That's our electrophilic part of the molecule. And then because carbon can only have 4 bonds, we have to break one of the bonds, and we break the weakest bond, which is the pi component of that CO double bond. And so we have an arrow going from the center of the CO double bond and ending up on the electronegative oxygen. The oxygen's happy to accept that electron pair because it's electronegative. It's happy to have that negative charge. Now remember that every step of a mechanism has to balance in terms of charge and in terms of atoms. So we've started off here with a negatively charged nucleophile and a neutral electrophile. So overall our molecule has to be negatively charged, and the negative charge goes on to our oxygen. That's the sort of most electronegative part of that molecule. So this is now our tetrahedral intermediate. We've gone from a trigonal planar molecule, carbonyl, to a tetrahedral molecule now. And so the second step of this nucleophilic addition is that isn't the final product. We have an O-, that's not particularly happy. Instead, we get some charge attraction going on. So simply the O- will pick up a proton, an H+ ion, from somewhere. It can sometimes be, if you've added a little bit of acid into your mixture, it can also be simply from water. But it'll pick up a hydrogen ion from the solution somewhere, and that turns it into an OH, an alcohol group. And so this is our nucleophilic addition mechanism. An arrow from the nucleophile to the delta plus carbon, an arrow breaking that pi component of the CO bond, and then finally an arrow from the negatively charged oxygen to a hydrogen ion. And so you can see this is very synthetically useful reaction. We've started off with a carbonyl, in this case a ketone, and we've converted it to an alcohol overall. So another example of this kind of nucleophilic addition reaction would be to use a cyanide anion, Cn-. And something to note with this is that the cyanide ion actually has the lone pair, a negative charge on the carbon atom, not on the more electronegative nitrogen. It's slightly odd in that it's on the carbon. But we could use a solution of sodium or potassium cyanide as a source of the cyanide anion, and then follow that by the addition of some dilute HCl. Remember that the HCl is just there to essentially give us a proton in order to turn our tetrahedral intermediate into our stable product. Now we could use HCN, hydrogen cyanide, in theory, but it's a very, very toxic reagent and it's also a gas, so it's much more difficult to handle than a solution of sodium or potassium cyanide. Now the products of this reaction, when we've done this nucleophilic addition reaction, is something called a hydroxynitrile. And this is because we have our CN group, our C triple bond N, that's a nitrile group, but we also have our OH group. And normally that's, as its alcohol group, it would be named using the suffix -ol. However, the nitrile group, the CN group, takes priority in the naming. And so here we have to use the prefix hydroxy instead. So this is a hydroxynitrile. Now hydroxynitriles are really useful in organic synthesis because they contain both an OH group and a cyanide group. And these are both very, very reactive. OH group obviously can be used in nucleophilic substitution reactions. Our cyanide group can be oxidized to a carboxylic acid. It can be reduced down to produce an amine. So both of these groups are very, very useful. Also, the length of the carbon chain has increased by 1. By using a cyanide anion, we've got a carbon in that nucleophile, and so our carbon chain increases by 1 when we do this reaction. So it's also very important for industrial chemistry. Now the reaction when we do this will produce a racemic mixture, a 50-50 mixture of the two optical isomers or enantiomers. Remember that enantiomers are stereoisomers. They have the same connectivity of the atoms, it's just the 3D shape is different. The sort of 3D arrangement of these groups is different. And so when we talk about enantiomers, we have this kind of, like your hands, non-superimposable mirror images of one another. And so I've drawn an example of it here. You can see that the molecule on the left and the molecule on the right are mirror images of one another. That's what the dotted line is representing, a mirror. And so if I was to literally superimpose those two on top of each other, they wouldn't be able to fit on top of each other perfectly. Now, if you're not quite happy with optical isomers and enantiomers, please do check out my video on optical isomerism. But the reason why this produces a mix of optical isomers, and specifically a racemic mixture, a 50-50 mixture, is because our aldehyde is a planar molecule. And what that means is that our cyanide anion, or whatever our nucleophile is, can attack from either above or below the plane of that carbonyl group. And so because it can attack from above or below in equal probability, we therefore end up with a 50-50 mix of those enantiomers. One where it's added from the top in 50% and one where it's added from the bottom in 50%. As this is a type of, we'd call this aldehyde something that we call prochiral. What we mean is that it can be turned into a chiral molecule in one step. Now, another type of reactivity that we see is oxidation reactions. Now, we've covered this slightly before if you've seen the video series on alcohols. And we know that primary alcohols can be oxidized up to aldehydes. But aldehydes can then be further oxidized up to carboxylic acid. Now, one of the common oxidizing agents for this is potassium dichromate, acidified with dilute sulfuric acid. That's K2Cr2O7/H2SO4. Now remember that secondary alcohols can be oxidized up and they form ketones, but ketones can't be oxidized easily to carboxylic acids, and they can't be oxidized further because we now no longer have any carbon-hydrogen bonds on the carbon that contains our oxygen. So in order to oxidize it further, we'd have to break a carbon-carbon bond. Now a carbon-carbon bond is fairly strong, and also it's a lot less reactive than a carbon-hydrogen bond, and so it can't be broken easily by many oxidizing agents. What can break it is a stronger oxidizing agent, a much stronger oxidizing agent than the potassium dichromate. But what this tends to do is actually break the carbon-carbon chain up, break the hydrocarbon chain apart, and produces smaller chain molecules, carbon dioxide and water. So that's not the reactivity we wanted if you wanted to oxidize it up to a carboxylic acid. So weak oxidizing agents will therefore oxidize aldehydes, but they won't oxidize ketones. And this is the reason for one of these distinguishing tests, how we can distinguish if we have two unknown samples, one of them's an aldehyde, one of them's a ketone, which one is which. And so there's two reagents that we can use. The first is Fehling's test. And so Fehling's solution is actually a mixture of two solutions that contain the copper 2+ ion. Now the copper 2+ ion is blue in colour. And it also contains an alkali, sometimes sodium hydroxide. And essentially, when an aldehyde is warmed with Fehling's solution, we get the aldehyde being oxidized up to our carboxylic acid. And remember that oxidation and reduction have to happen together, this redox process. So if we've oxidized up our aldehyde to a carboxylic acid, our copper 2+, which in this case is copper hydroxide, gets reduced. And we end up producing copper 1 oxide, and this is a brick red precipitate. So if we have an aldehyde, what we would see is the blue solution, copper 2+, turning into the brick red precipitate of copper oxide, copper 1 oxide. Our aldehyde gets oxidized to a carboxylic acid, and the key thing is that ketones don't give a reaction to this test. So if we sort of warmed a ketone with Fehling's solution, there'd be no change. We'd still have that blue solution of the copper 2+. Now the other reagent that we can use is something called Tollen's reagent. This contains the silver complex ion, AgNH3+. This is formed when we add aqueous ammonia to silver nitrate. And when an aldehyde is warmed with Tollen's reagent, again, because the aldehyde can be oxidized up to our carboxylic acid, that happens, and therefore we actually get reduction of that silver complex ion, and the reduction that takes place is to reduce it down to metallic silver, actual metallic silver. Now ketones give no reaction to this, again, because they can't be further oxidized up to the carboxylic acids, and so what we see is if we warm an aldehyde with Tollen's reagent, we get our aldehyde being oxidized up to our carboxylic acid, and our silver complex ion, which is colourless, being reduced to metallic silver. So it's literally that sort of metallic coating that you get on the test tube. Ketones, there'd be no reaction in, so you'd still have a colourless solution. Now, the other type of reaction we can look at is a reduction reaction of our carbonyl group. So many reducing agents will reduce both aldehydes and ketones to alcohols. And the one that's really important to know for A level is sodium borohydride, sometimes called sodium tetrahydroborate, or more commonly sodium borohydride in aqueous solution. And it essentially generates the hydride nucleophile, an H- anion. So now we're used to seeing H+ cations, a proton. Now we have an H-, a hydride anion. This is a hydrogen atom that has gained an electron. And so it contains 2 electrons. It has a lone pair. Now, there's an important distinction to make. Essentially, this generates the hydride nucleophile, H-, but if we're drawing our mechanism out really properly, we should start by using this actual sodium borohydride. So this is an ionic molecule. We have our sodium positive cation, and then our borohydride anion, BH4-. Now, the thing to note is that quite often we draw our arrows in mechanisms from a negative charge, because normally the negative charge, for example, on a cyanide anion or on a hydroxide anion, represents a lone pair. In this case, the negative charge does not represent a lone pair. And the reason for this is because if you work out our electron configuration, boron has 3 electrons. It can form 3 covalent bonds to hydrogen to make BH3. This is an electron deficient molecule. It only has 6 valence electrons. And so to create the borohydride anion, BH4-, we have to have a coordinate bond forming from a hydride anion, H-, to the boron. The boron doesn't have any electrons left. It can't form any more normal covalent bonds. But if we have a hydride, something with a lone pair on 2 electrons, This can form our coordinate, our dative covalent bond, where we give both electrons from the hydride to the boron, and this creates BH4 minus. But the key thing is that our boron has 8 electrons now. It doesn't have a lone pair. All of those 8 electrons are used in the BH bonds. So the nucleophilic part of the molecule is not a negative charge. It is the BH bond. It's the electron density in between a BH bond. So just double check with your exam board as to whether when you draw out the mechanisms you can draw it out as the hydride nucleophile H-, or whether you need to draw it out as the BH4 anion. If it's the H- nucleophile, then you can just draw an arrow from the negative charge of your H-. If you're using BH4-, you have to draw the arrow from the BH bond. But at the end of the day, it's still essentially a nucleophilic addition reaction, so the mechanism is exactly the same as we've seen before. We take borohydride anion. Here I've drawn it as the BH4. So from the BH bond, an arrow going to our delta positive carbon, our electron deficient carbon, because of that really strong dipole. And then a second arrow. The carbon already has 4 bonds, so we have to break one. We break the weakest bond, the pi component of that CO bond. And so we have an arrow from the CO double bond ending up on the oxygen, the electronegative atom. Then we create our tetrahedral intermediate. And so the second step is then the same. We'd have some protons somewhere, maybe sometimes from water, if it's an aqueous solution. And so our negatively charged oxygen just picks up a proton, and then we end up, in this case, having gone from a ketone to an alcohol. And the same thing would have happened if we started with an aldehyde. So the sodium borohydride will reduce ketones and aldehydes down to alcohols. So it reduces the polar CO bond, and the reason for this is because it's attracted to the delta positive carbon, but it would be repelled by the high electron density of a carbon-carbon double bond. So it's the reason why we can't reduce a carbon-carbon double bond down to a carbon-carbon single bond using sodium borohydride. We have to use a hydrogen and nickel catalyst to do that. And the reason is this reducing agent essentially is acting as a nucleophile. We know that alkenes have a really strong region of electron density between the carbon-carbon double bond, and so that's also quite often a nucleophilic component, and so we have 2 regions of high electron density that would be repelled. In this case, we have our nucleophilic borohydride anion, and then we have our electrophilic carbonyl group, very strongly electron deficient delta positive carbon. And so aldehydes get reduced down to primary alcohols, ketones get reduced down to secondary alcohols. And again, it's a nucleophilic addition reaction. So, time to have a go at some questions. If you'd like to have a go, pause the video and the answers will be on the next slide. But we have some naming questions to do, drawing the mechanism for a couple of different things. One of them is using HCN, and the other is using sodium borohydride. So the first question was to name the following molecules. So we're always going to use our standard IUPAC naming. Look for the longest chain, note where any substituents are, number the substituents, number everything that we have to, and name it in alphabetical order, not numerical. And so our first molecule here, we're going to look for our longest chain. Our longest chain is 5 carbons long. Remember that we count the carbonyl carbon as part of that chain. And this is an aldehyde, right? We have our CO double bond connected to a hydrogen on one side and a carbon group on the other. That's an aldehyde. And remember that we don't have to number our aldehyde because it's always going to be at the end of the chain. So it's a 5 carbon chain, so we know that the end of our name is going to be pentanal. Remember that we name aldehydes with the suffix -al. And then we just have to note where our substituents are. So the aldehyde group always takes priority, that's carbon number 1. So we have a methyl group on carbon number 2, a bromo group on carbon number 3, and a hydroxy group on carbon number 4. Note again that we have an OH group, which is an alcohol, normally named with the suffix -ol, but because we have the aldehyde, which is more important, that's got the suffix in the name, we have to use the prefix hydroxy to name our OH group. So the name of this would be 3-bromo, 4-hydroxy, 2-methyl pentanal. Note that it's in alphabetical order, not numerical. The second molecule, again, look for the longest chain. Again, it's a 5-carbon chain. Now here we have 2 ketones, so we have our carbonyl group with carbon groups attached to either side. Remember that we're going to have a standard IUPAC rule, so if we have multiple of a functional group, we have to use the di, tri, tetra naming. So this would be something that we call a dione, a diketone. We have to number where our ketones are. So the ketones are on the second and the fourth carbon. It doesn't matter which way which direction we number from, it's always the second and fourth carbon. And then we have a bromo group in the middle there on the third carbon. And so this would be called 3-bromo pentan 2,4-dione. Question 2 was to draw the mechanism for hydrogen cyanide reacting with our ketone. Our ketone in this case is propanone, our simplest ketone, and we're asked if the product was chiral. So this is a nucleophilic addition reaction. So we take our cyanide anion, we draw an arrow from the nucleophilic part, which is the negative charge, to our delta positive carbon, our electron deficient carbon, that's the electrophilic part of the molecule. And then, because carbon already has 4 bonds, we break the weakest bond, the pi component of the CO bond, so an arrow from the middle of the CO bond to ending up on the electronegative oxygen that's happy to accommodate those electrons. Again, remember that our charges must balance, so we had a negative charge overall in the first step, so we have a negative charge on our oxygen in the second step. And then we just pick up a proton, which could be from some dilute acid, it could just be from water. But we pick up our protons, so our negatively charged oxygen, arrow from there to the H plus cation. And this ends up producing our, what we called a hydroxynitrile earlier. If we wanted to name this molecule, we'd look for the longest chain, and we include our nitrile group carbon in this. So this is a 3-carbon long chain. The nitrile group takes the priority, so that's carbon number 1. So then on carbon number 2, we have a methyl group branching off, and we have an OH group. Again, because the nitrile group is the important one, we have to use the prefix hydroxy for the OH group. Name it in alphabetical order, so it's 2-hydroxy, 2-methyl, propane nitrile. Now, is the product chiral? Remember, for chirality, for chiral molecules, we need to have 4 different groups attached to our carbon. And you can see here that our sort of central carbon in this molecule has an OH group, a CN group, but then 2 CH3 groups. So there's not 4 different groups attached, and therefore this isn't a chiral molecule. Question 3 was to draw the mechanism for the reaction of our aldehyde plus sodium borohydride. So this is, again, a nucleophilic addition, but this is now a reduction reaction. And so we're going to draw out our aldehyde. Now note, in this molecule we have a CC double bond and we have a CO double bond. Now we could reduce either of these, but the reagent we've chosen here is our sodium borohydride. And remember we said that our sodium borohydride is a nucleophilic reagent. It's an electron rich, essentially the hydride anion H-. We have our CC double bond, which is also a region of electron density. So sodium borohydride won't reduce down the carbon-carbon double bond because it would be repelled. There's lots of electron density repelling each other, but it's attracted to the electrophilic carbonyl group, our delta positive carbon, electron deficient carbon, because of that electronegativity difference between the carbon and oxygen and the strong dipole produced. So the same mechanism as before, we take our arrow from our H- here. I've drawn it as an H-, not as the BH4- anion. So if we're using it as H-, we can just draw an arrow from the negative charge on the H to the delta positive carbon. Then break one of the bonds. It's the weakest bond that breaks, so the pi bond of the CO double bond. So an arrow from the middle of the CO bond ending up on the oxygen. We then have our, make sure that our charge is balanced, so we have to have our negative charge on our oxygen, that's accepted at the electrons. And then I've written here an H2O workup. It could be H+ from water, it could be H+ from some dilute acid, but it essentially picks up a proton, and we then end up forming our OH group. And so the name of this, if you're asked to name it, is but2n1ol. That looks slightly odd. The reason for that is because we have our alcohol group, and the alcohol group here is the important one, so we do have the suffix ol, and it's on the first carbon. But we also have our alkene section, which we normally denote with the suffix ene. So essentially we kind of combine them together. It's a 4 long carbon chain, so it's but. If it was just a 4 carbon chain with an alkene, we'd call it but2ene. But because we have our alcohol as well, we essentially combine the 2 names together and get but2n1ol. And if we wanted to reduce the CC double bond part of it, we'd have to use a hydrogen and nickel catalyst in order to reduce that down. So thank you for watching. I hope you found this video useful. You can find lots more like it on my YouTube channel. If you have found it useful, please leave a review on one of my tuition websites. I offer online tuition for chemistry, so check out the tuition pages if you're interested in that. And if you need any more help with your chemistry, feel free to drop me an email. I'll be happy to help.